Without further ado, I would like for you guys to give a warm welcome to Xiaorang Wang, which is going to be presenting today RAVAGE, Runtime Analysis of Vulnerabilities and Generation of Exploits. Thank you so much.
All right, can you guys hear me? Cool. All right, welcome to RAVAGE. My name is Xiaorang Wang, and I'm a security researcher and an engineer in Salesforce.com. And I'm supposed to have a partner here, but because unfortunately he was overexcited, drank too much, and passed out. So he wouldn't be able to be here to present. This is how you feel when your partner abandons you in the last minute. Joke aside, he got some last minute changes, he has to go, but I will be presenting here for myself. Okay, so here's a quick rundown of what I'm going to talk about. First of all, I'm going to talk about why we're here, why we need another tool, and why the current tools are insufficient for vulnerability detection. And then I'm going to talk about what is RAVAGE and how it's designed, and give you a quick demo of how you can use RAVAGE, and then how RAVAGE looks like. And then I'm going to talk about how RAVAGE is actually being implemented in the weeds, and then give you a full demo so that you can see more power unleashed from RAVAGE. And then I'm going to talk about how you can use RAVAGE in your own company, in your own product, and detect vulnerabilities, and then, if you like, generate exploits. At the end of the day, what I wanted you to take away is some in-depth knowledge of runtime analysis, and in the meantime, a tool you can take home and play with. So let's start the journey. We have a lot of tools, all kinds of tools. And we have static analysis tools, a lot of vendors. We have black box tools, a lot of vendors. So static analysis claims to be scalable, and we have a quote for that. In the meantime, they also claim to be accurate. They can detect all kinds of vulnerability with high confidence. They also claim to be easy to use, where we also get a quote for that. So what about reality? In reality, things are always different from what it claims to be. For example, I would say they're not so scalable. If they come across complex code bases or library dependencies they can't figure out, they're not very good in getting a lot of real issues. And also, I would say they're not very accurate because if you have things like reflections, interfaces, and all of those, they have to get runtime information to talk about, then static analysis always fail to do that. And they're not very easy to use. When you have static analysis scan your application, you get a lot of results. However, in the meantime, when you're reviewing those results, you have no idea which URL triggers the vulnerability, which parameter triggers vulnerability, and then whether they're actually reproducible or not. And usually at the end of the day, most of them are not, but you just don't know. You have to go through them. So those are actually kind of pain that we went through in our team. And then let's talk about black box. Quickly, they don't have knowledge of the app. And they can't deal with multi-stage requests, where they're struggling with the wizard-like pages and stuff like that. They also rely heavily on the response data from server. So if there's a vulnerability on the server side, it's purely on the server side, and it doesn't respond too much data to the attacker, it's really hard for the black box tool to actually tell whether there's vulnerability or not. There's no code coverage because it's a black box. There's no data flows because it's a black box. And it could be potentially disruptive because all of the attack data that the tool sends to your server. And here's another interesting quote we got regarding the two tools. So they say those tools can be really seductive because they do find a lot of vulnerabilities. However, when you go through every single one of them, you spend a lot of time. And at the end of the day, you got 99% of them are false positives, and only 1% are real issues. So here we see a problem. And how do we solve it? We have runtime analysis. So runtime analysis is not a new topic. It's only relatively new compared to static analysis or black box tools. And just a quick background of what runtime analysis is. It's basically trying to monitor a program at runtime. And it tracks data from tainted sources to tainted sinks. It's basically a form of taint analysis. And you can detect vulnerabilities such as XSS, simplest like XSS, SQL injection, and static encryption keys, or secret leaking to logs, or more complex issues such as if you have a multi-tenant application where you do not want user A's data leaking to user B's zone. So you can easily tag your data and say that data is from user A and never let it to go to other users unless you allow it to. So those are always any kind of data flows, vulnerabilities associated with data flows. And even control flows, we have ways to track it in runtime analysis as well. So what are the advantages of runtime analysis? We have a few of them. For example, it definitely has a very low false positive rate because everything at runtime is actually what program can run at runtime. And also, you don't need exploit data because runtime analysis runs purely on the taintedness of data. As long as data is tainted, we tag it, and we know it's a vulnerability. We don't need source code because it's runtime analysis. And it can leverage existing testings. So this I will talk about more in the future in the integration part because it will be really exciting. And if you design correctly, it's also able to get complete data flows. And we're going to talk about what is complete data flow and what is correct data flow. So there are many tools that does runtime analysis, but most of them do runtime analysis on native applications, like x86 applications on different operating systems. But we didn't find too many tools that does runtime analysis on interpreted languages, for example, Java. So there were a few applications that does Java runtime analysis, and we examined a few of them, but we found some problems. So some of them doesn't have data flow at all. And what you see after you detect a vulnerability is the source of the taint and the sink of the taint. You have no idea how the data can traverse from the source to the sink. And why that is a problem is because if your program or application is really large, you always have those simple sources, simple sinks, no matter what vulnerability it is, no matter if it's XSS or what kinds of XSS, it's always going to come from the same source and the same sink. And there also could be multiple vulnerabilities that share the same source and the same sink. And also it could be tens or hundreds of different possible paths you can come from that source to that sink. So obviously, you have no knowledge of how your data goes in your system. It's basically really close to a black box tool. And then some of them have incorrect data flows. I will talk more about what is a correct data flow means, but if you think about it, data flow is completely different from stack trace or control flow. And how to get a correct data flow is very challenging. And some of the tools do have correct data flows, but only on very limited objects. For example, strings or other immutable objects. As we'll talk about later on, immutable objects are really easy to track data flows, but mutable objects are not. And I will explain why later. Here we have a few graphs that compares quickly static analysis, black box tools, and runtime analysis. If you imagine the graph on the screen as your application, the bottom it is, the deeper the program can be penetrated with the tool. So if you take a look at static analysis, it has a bunch of green dots. And the green dots means real vulnerability detected. So it's able to go deeper into the program, but also it suffers from those red dots, which means false positives. And black box tool works different. It detects a bunch of issues on the surface, but not too deep in the program. And also you start to see false negative because black box doesn't understand your program at all. And then here's the beauty of runtime analysis. You're able to go as deep as static analysis because you understand the program. In the meantime, because this is a runtime, you don't have too much of false positive. That is a great thing. So does it mean that runtime analysis is always better than static analysis or black box tool? I would say it depends. If you do have a good test coverage, a good driver that can drive a runtime analysis tool to run different paths in your program and to discover as many vulnerabilities as possible, I would say runtime analysis will definitely detect more vulnerabilities and less false positives. So before going into how RAVAGE is designed, let me show you some figures. We experimented with running RAVAGE and also a static analysis tool and a black box tool against a few web applications. Unfortunately, I can't show you exactly which are those because we found vulnerabilities, reported them, but they're not fixed yet. But I can show you the statistics. So first of all, we only limit the scope to be a few vulnerabilities, XSS, arbitrary redirection, and a few injection flaws. And the reason for that is that for RAVAGE, it's still a new tool, and we don't have a very rich rule set yet. So to have a fair comparison with other tools that are much mature, we only limit the scope to the rules we have. So here are some figures. On average, for static analysis, it reported 150 issues in total, and 14 of them are real issues. Basically, 90% of them are not real issues, are false positives. And false negative is 8%. And how false negative is calculated is basically the number of vulnerabilities detected in one tool over the totality of all tools, of all vulnerabilities detected by the 3 tools. So there might be more vulnerabilities, but we didn't have time to go through a full review to find all of those. And then we have black box tools. Black box tool, on average, detect less issue than static analysis, also has less real vulnerabilities. As for false positives, it has around the same level regarding static analysis, but also has high false negatives. But black box tool does finish scanning much earlier than static analysis, so that is a plus. Then we have RAVAGE. RAVAGE, if you see the figures, it detects much less issues compared to the previous 2 tools. However, among the issues it detected, almost all of them are real issues. So the false positive rate is really low. It is around 15%, and the false negative rate is around 27%. So we can still improve the rate on the false negative. And the reason for the false negative to not be so low is that we didn't have a good driver to drive RAVAGE to scan those applications. And what we did is basically just some manual usage of the application with some burp or black box testing tools drive usage of the application. So we didn't actually have time to go to every single corner of the application to scan it. But if we were to have a good test coverage or a good tool to actually drive the application to run different corners, we would have been getting a very low false negative rate. So the summary of that is that RAVAGE can detect vulnerabilities with a really low false positive rate, and also can have a really low false negative rate if you do have a good test coverage or driver to drive it. Okay, now let's talk about what is RAVAGE. It could be that for 1 second. It could also be that. So RAVAGE represents runtime analysis of vulnerabilities and generation of exploits. It's our implementation of runtime analysis for Java. It's open source, it's free, and it's around 5,000 lines of code. And it's written mainly in C, C++, Java, and assembly. On a very high level, how it's been designed is that we want to track all relevant operations, no matter it's a function invocations or returns, or it's a field accesses or storage, or it's assignments from one object to another object, or it's a retrieval or storage, or any other kinds of operations. We track those operations and we store the data flow, a data point, into a node object, and that you will see on the slide as a node. So in the node object, what do we actually store in there? What do we mean by data point? By data point, we mean where exactly in the source code does this particular point in program represent? Which source file, which line, where in the program does it mean? So that we record a data flow, a data point. And then not only data point, we also record context information. For example, where did you get attained? Did you get it from a user? Did you get it from a database? Did you get it from a URL? Did you get it from a file? Or is it HTML escaped? Or is it JavaScript escaped? Or is it SQL escaped? Or anything. And all of those are encoded into a flag that user is able to customize. And then we store the node object into the original object that we're tracking data flow with, so that we do not want to create a separate map just to track data flows, because that would be really messy and hard to maintain. And here's the interesting point. We split objects at each data point. What we mean by that is that if you have a function call, say full, and you pass a string s, instead of passing the actual string s, we create a copy of a string s and pass that to the full function. The reason we do that step is that we want to decouple different data flows of different paths in the program to be separate from each one. Otherwise, the data flows in different paths are going to mingle together and then create false positives and false negatives. And then at the end of the day, you want to chain all the nodes together to create a complete data flow graph so that you know exactly how your tainted data traverses in your system. So let's talk about data flow. I talk a lot about data flow, data flow, data flow. So what does that mean? What do we want to get exactly in a data flow? Everybody likes math. Here's math. I personally don't understand what it means at all. It's basically ciphertext to me. It's indistinguishable from random characters. And what I do understand is that we want to track all relevant nodes, but no extra ones. And what do I mean by that? Let's take a look at this very simple example, 7 lines of program. Here we have a very simple XSS where on the first line we get a string from request, and then second line we pass it to full function. In full, we print a static string welcome and returns. Line 3, we pass string to bar. Line 6, we print a string into the print function or into the response. So if you take a look at data flow of this XSS vulnerability, what happens to that string is that at line number 1, you get the string. Line number 2, you pass the string to full. Line number 3, you pass the bar. And line number 6, you print it out. So you have 4 data points. But is that a correct data flow? I would say it's not. Because why do we care about a function full? Whenever you pass into a function full, it doesn't do anything about it. It doesn't change the string. It doesn't change the taintedness of the string, or untainted or tainted, or it doesn't change the context of it. It just doesn't do anything. So we do not want to have number 2 to appear on our data flow. And what we do want to get is only line number 1, 3, and a 6. So that's what I mean by correct data flow. Just a very simple example. If you take a look at 1, 3, 6, is it a stack trace? I would say no. Because if you were on line number 6, the stack trace would have been only 6 and 3. There's not going to be line number 1. So that's how you can tell the difference between stack trace and data flow. Then let's talk about another example. Also very short, 7 lines. You get a request you get a string from request, and then you create an object, and then you pass that string, assign it to the object, and then you pass the object to 3 functions incrementally, and then at the last function at 3, you get a string out and print it out. So if you follow the paradigm that we did in the previous example, the data flow would have been line number 1, where we get a string, and then line number 3, where you assign it to an object, and line number 7, where we print it out. So okay, 1, 3, and 7. Is that enough? I would say no. Because how would I know how line number 3 can reach this line number 7? Imagine in your application, there could be tens or hundreds of functions in between 3 and 7. And how would you know exactly whether that is actually reachable or is false positive or not? So we do want to also include 4, 5, and 6 in data flow. But those data flows are not for the string, right? Because those have nothing to do with the string. Those only deal with the object. So how do we do that? We have to somehow chain together different objects' data flow in order to create a complete data flow for a particular object. And that is what I meant by complete data flow. So you can sort of tell the complexity of when you're getting data flow and how you can get a really good data flow you want. So that's one of the design questions we got. We said, I talked about storing stack trees is really easy, and data flows are not. What about others? We talk about tracking events. Maybe tracking some events are easy. Like there are existing tools that track function invocations and returns. In Java, for example, there's Java Agent, there's AppSec. You can always do that, really easy. But what about other tools? What about other tracking events? For example, Simon's, control flow, if-else, switch, all of those. We didn't find a good tool or framework that does that. And even if we do have that, what about performance impact? Because think about it, at every single tracking event, you're doing a lot of things. You're trying to track data flows, you're checking rules, you're creating a copy of objects, you're basically doing a lot of cleanup. So adding all of those workflow to your program at every single stage of the execution it's going to be really, really performance, going to bring up really a lot of performance hit. So we also talk about splitting objects, right? We create a copy of object whenever it reaches different parts of the program during tracking events. Then split some objects such as string as set is easy because string is mutable. If you create a copy, use it later, no worries. They're always going to stay the same. But what about mutable objects like string buffer, string builder, all of those? Are you able to actually split those objects? You probably are, but the thing you have to worry about is that you have to maintain consistencies. Because whenever you create a copy of those objects will go to different parts of the program, and in order for the program to function still correctly, you want to maintain the same data in those all objects. And things grow exponentially really fast. And how do you do that? And there's also other objects that you cannot really split. Like, for example, single objects or resource-bound objects. Those are intended to have only one copy in the system. So how do you actually create a second copy? And when you're creating so many copies of objects, like, it's going to be insane on the memory cost. Like, if you create a string that's 100 bytes and duplicate, it's going to reach like a few gigabytes really soon. So how do you tackle that? And we also want to be invisible to the program because we do so many things to the program, and we want to make sure that all the things we do, the program is not aware and still able to function correctly. So instead of going into all the design decisions we got, let me introduce one of the design decisions we got, which we call wrapper. So if just FYI, if my partner were here, he was supposed to wrap the rest of the presentation. I wouldn't do that myself because you guys would just stand up and leave. Let me do that again. Introducing wrapper. So wrapper is a simple, but we think is a clever way to track data flows. What we do is that we wrap each object with a wrapper and store the reference to the original object in the wrapper itself. And inside of each wrapper, instead of storing the node in the original object, we put it back into the wrapper. So the original object is intact. And everything that we care about data flow is in the wrapper. So think about object splitting. When we're splitting the objects, now we're not actually creating a copy of objects. We're only creating a copy of the wrapper, which should only have 2 memory references. So it's only going to be like 8 bytes of memory or 16 bytes of memory, depending on which platform you're on. So it's going to leave very little memory footprint. And also, in the meantime, it solves the problem of maintaining consistency of mutable objects and also those singleton and resource-bound objects. We don't have to care about those at all. Everything is abstracted out into the wrapper. So that looks working, right, on the design level. But if you think about changing every object in Java to wrapper, I think things are going to be really funny because Java is a type-safe language. Let's see how that goes. And before I go into the real implementation, let me give you just a quick demo of how RAVAGE looks like and how it's like using it. So again, can you guys see the screen there? OK, I can see it. So again, we're not able to demo real applications because those vulns are not fixed yet. But instead, we are going to show you a demo of running WebGoat on RAVAGE. So WebGoat, for those of you who don't know, is basically an intentionally insecure application for people to play with and learn about web security. So here we have WebGoat running on Tomcat that is running on RAVAGE. And before I click into WebGoat, let me show you something here. So here is a thing called Honey Badger. It's our colleague Travis' effort role for auditing security vulnerabilities whenever it's reported to that engine. So what RAVAGE does is that basically on every detection of vulnerability, it uploads the issue to Honey Badger so you can view that in real time in your browser. So let's see how RAVAGE can detect vulnerabilities. Let's refresh. And let's keep refreshing. In the meantime, let's go to WebGoat. Okay. Things get really slow, always, at the demo. So let me just refresh it again. Yeah, now it's there. Project list. OK. That actually doesn't look right. Okay, let me fix something really quick. I better stay there. Let's see whether it's up. Yes. So let me kill the existing process. Let's run a new one. See, no matter how many times I practice demo, we never know it's not going to work at runtime. It's the beauty of runtime analysis. In the meantime, let's kill the original RAVAGE process and start it again. So if you take a look at it, it's basically an example that runs on Tomcat of RAVAGE, where RAVAGE is basically a special version of Java. Let's go back to Honey Badger. Okay. Instead of wasting you guys' time here, waiting for it to load, let me show you a quick demo in video that I know I recorded and it should be working. So what I originally wanted to show you, is that I wanted to click on some links in WebGoat, and then whenever I was using RAVAGE while using WebGoat, RAVAGE should be able to detect vulnerabilities automatically. So those existing issues are there before I started WebGoat, so let's ignore that for now. And we will see there are going to be more issues detected when we're using WebGoat regularly with RAVAGE. So this page is a simple cross-site scripting where if we search anything, the search text reflected onto the page will not be encoded. So classic XSS. If you refresh the Honey Badger, you're going to see another cross-site scripting recorded in there. And if you can see the issue there, it's basically a full data flow from where you get the source to where you print it out to the program. And let me pause it very quickly. So on the top left corner, let me just expand it very quick. On the top left corner is basically the RAVAGE output. You can see it's basically a JSON object that contains all of the data flow information and also the vulnerability. It's a cross-site scripting and has all the traces. And then on the bottom of it is basically the age part from RAVAGE. You know, RAVAGE is runtime analysis of vulnerabilities and then generation of exploits. So the bottom part is the generation of exploits. So basically we have something that will detect XSS, and once XSS is detected, we'll try to generate an exploitable URL that will be automatically tied to Beef to exploit a browser. So for those of you who don't know Beef, Beef is basically a browser exploitation framework that exploits your browser through a cross-site scripting vulnerability. So if you can see on the bottom left-hand side, it's basically exportable URL that our engine just generated, and will show you how that's going to be used to exploit your browser. So let's take a look at the Beef control panel. There's no online browser yet, meaning that there's no browser being exploited yet. But let's go to that URL. And again, if you go back to Beef and refresh it, you're going to see a new browser being hooked. Is the Firefox we just used in WebGoat. And that's just a quick demo that I wanted to show you. In the meantime, let's just check very quick and see whether Honey Badger is up. Nope. Demo God is not with me today. So I'm going to show you more demos later on in video. OK. So now you have a quick look at what is RAVAGE and how it detects vulnerabilities. But those are very limited because you just only use it manually to detect it. And later on, we'll show you how you can use it automatically to detect all kinds of vulnerabilities. So going back to the implementation, how did we implement it? On a very high level, it's straightforward. when we tried our first attempt, we wanted to just keep it simple. Let's modify the Java bytecode, and let's see how that goes. So what we did is that we inject a bunch of RAVAGE hooks to the Java class files, and the hooks will do a bunch of things, such as wrapping objects, checking for rules, and then gathering data flows. So that sounds straightforward. Does it work? Sometimes, not always. We got a lot of problems when modifying the Java bytecode. And most of the reasons is because, remember the wrapper thing, right? We change every object's type to be wrapper. And that doesn't work too well in Java, especially when it does type checking, type enforcement, and everything like that. JVM was like freaking out when we were checking everything to wrapper. It crashed every single second. We were like, OK, that's not going to work. Let's try something different. And here's the sad cat after we failed that. Second attempt. So we thought about the problem, and most of the reason was because the JVM was giving us trouble. So we thought, why not we go a deeper layer and modify the actual JVM? So let's go about doing that. A quick background of JVM. The JVM interprets Java bytecode in the class files, and the one we modified in the OpenJDK's JVM, and it has two interpreters. One is called C++, one is called template. So the template is the one being used, and it's written entirely in assembly code. So, and the one we modified is the OpenJDK's 8 JVM. So it runs basically Java 8. And on the design level, it's really similar to how we did to the Java bytecode. Instead, we just did it to another lower layer in the JVM. So in the interpreter, we inject a lot of hooks. In the meantime, the hooks does the similar things to what we did in Java bytecode, track data flows, track rules, and do all sorts of things. And again, looks working, right? As usual, as my demo is supposed to work. But we face a lot of challenges. So first of all, the JVM is really, really complicated. It's basically the operating system. 250,000 lines of code. We have to understand it. And it's mostly self-documented, if you know what I'm talking about. So there's a lot of optimizations and tweaks we have to take into account. Otherwise, we're going to ruin the whole runtime. And it's really painful to debug assembly code. Have you guys ever tried about using GDB to debug Java? No, right? This sounds absurd. But that's how you do when you debug JVM when running a Java application. You have no idea where in Java is, but you want to know. You just live in the constant pain of not knowing where you are. And how do we solve it? As usual, beer. So after a lot of beer and drunk times, we finally implemented it. But before we did our implementation, one question we thought about is that, where do we want to implement RAVAGE? We talk about modifying the interpreter, but it's all assembly code. We didn't want to write a bunch of assembly code. It's hard to maintain, hard to debug. We were like, why not we just insert a tiny hook into assembly code and call out to Java to handle whatever logic we have? It sounds straightforward, right? It sounds should be working. And we called it to Java. And we got 420 times slowdown. For those of you who are not good at numbers, what it means is that if you want to try to start a Tomcat with RAVAGE, what you can do after you click on the start is that you can go out, have lunch for an hour, go to a coffee shop, look at some cat pictures, drink coffee, come back to work, talk to a colleague for another half an hour. After around 2 hours, is about close to finish starting. But things can get worse. What if the start crashed in the middle, just before the 2 hour? So what we got is that we have around 4 chances to start on the 8-hour workday. So think about it. Every day we go to work, start it, drink coffee, come back, crash, fix it, start it. What our bosses see in his eye is basically we're just walking all the day, no work. So it's to an extent that we're close, pretty close, I'm pretty sure, to be fired. So that's not going to be sustainable, mainly because we're not be fired. And let's fix it. We analyzed the problem, and most of the reasons is because we insert a bunch of Java code whenever we interpret Java code. It's like insert another layer of interpretation when we're interpreting one code, and that's not going to work. OK, let's take the pain and write it into C or C++, or the basically language that JVM is written in. And then we got back to 50 times slowdown. Great, not best, but still great. OK, so we were like, OK, let's not stop there. Already make performance boost, and maybe there's something more we can do. Maybe if we write it to assembly, that may be faster, and it is faster. Now it's 20 times slowdown. So we know it still has a performance impact, but it's not as bad as before, especially if you say compare it to other tools for analyzing memories on native applications like Valgrind or stuff like that. There's going to be also 10 to 40 times slowdown when we're analyzing mem checks or stuff like that. It's going to take time and take resources. So we know there's kind of room to improve, but it's not bad to start. And the room that I was talking about is that we didn't modify the JIT compiler. So for those of you who are not super familiar with the JIT compilation in Java, it's basically Java tries to compile your bytecode directly into native code and execute that. And if we modify the JIT compiler to be RAVAGE compatible, that's going to give us another 10 times boost, which is going to be the future work for RAVAGE. So RAVAGE does vulnerability detection, but what about after detecting vulnerability? There's few things you can do, or everything you want to do is up to you. RAVAGE exports plugins that you can write to handle vulnerabilities. You can audit it. You can store it for later auditing, or you can generate an exploit, or you can directly exploit it. It's up to you. And the interface is all going to be in Java. So you can write Java codes. It's going to be running a separate thread that handles vulnerability. So the one that I just showed you quickly is called Honey Badger plugin, which is basically a plugin that gets vulnerabilities and display it in your browser for you to audit. And there's another plugin that I also showed you. It's called Beef plugin, which after a detection of XSS is going to generate exportable URL and send it to the user and phish him. So this is going to be awkward because it's going to be another video time that I didn't anticipate, but let me show you another demo. So in the previous demo, we manually use RAVAGE to click on links and try to detect vulnerabilities, and we detect some vulnerabilities, right? But that's not going to be scalable because in your application, it might be a large application, and you might have a bunch of links and paths that we have to explore in order to find vulnerabilities. So how do we drive that? So in the demo that I'm going to show you, we're going to drive RAVAGE with burp and use burp to spider the website while the website is running on RAVAGE. So you will see when burp is scanning the website or the spidering the website, the RAVAGE will be able to detect vulnerabilities at real time without attack data. And then for added fun, now basically before I go into it, here just show you before we go to RAVAGE detection, we have like say 2 vulnerabilities detected. But we'll see more after we use burp as the black box tool to spider it. So here, what we want to do is just generate a few links for burp to work on. So it has some knowledge of the app and can start spidering it. So we want to try a few XSS and a few SQL injections, some XPath injection, and some of them are blind, some of them are deterministic. Just generate a few links. So the reason we chose burp is that burp is one of the state-of-the-art scanner in black box. So I want to compare it and see which one looks better and how we can use burp to drive it. So if you see, just after a few mouth clicks, we found another XSS. And if we start to use burp to spider the website, you can see on the left-hand side, it's trying to detect pop vulnerabilities. And out of this big chunk of JSON data are vulnerability traces. So here's just submit a regular form. And you can see all of the things popping up. And on the left-hand side is all of the XSS detected and all of the exportable URL that it's able to generate. And if you go back to Honey Badger and refresh the page, you see new vulnerabilities detected. So more cross-site scripting, more SQL injection, more XPath injection. You can safely ignore the print to console. It's just a debugging option that we used. And before we go into detail, let's actually start scanning with burp, and then we can compare the results. And during the scanning process, we can go back to Honey Badger to actually go into one of the vulnerability and see the data flow. So you see the scan queues running, and let's just audit the issues. So if you take a look at one example, where if you see on the left-hand side, it's basically the phishing.java 151 is the source of the vulnerability in your code. And the parameter parser.java line number 615 is the sink of the vulnerability. And in the middle pane is basically the complete data flow. You will see where you get the data from request. And then you retrieve the first element from that tainted array. And then you return it for whatever it calls the function. And then return again and assign the return text into a variable called search text. And then later on, we use the search text to create a string element. And the string element, at the end, you will see, will be added to the element container, which we define as a sink. So if you take a look at it, we have a complete data flow, but that's not only the thing we have. We also have the URL, right? And the parameter that make the vulnerability where we got the taint. So all of those, the URL, the parameter, you cannot get from static analysis. And data flow, you cannot get from black box testing. So it's basically the mixture of everything you can get from all those different tools. So that's probably going to go to a different vulnerability, but for sake of time, let's not go through it. So, OK, now Burp finished scanning. And what Burp found is some issue like clear test submission password and other or minor issues. Sometimes we're able to find one XSS, maybe one XPath injection, but it's kind of flappy. So now you can sort of see how much Burp is able to find and how much Ravage is able to find and get a comparison. So I apologize again for the live demo not being able to work. Never happened, never expected it. I'm glad that I took a video. So now you have some knowledge of Ravage. And I'm going to talk about, most importantly, how you can use Ravage for a product in your company. So if you have other tools already, say static analysis, great. It's not abandon it. We can run Ravage and SDA and cross-verify the results. Or you can use Ravage to verify the results of SDA and see if that works. In the meantime, if you also have black box tools, you can use the black box tool to drive Ravage to run, as I did, and also use Ravage to get data flow of the vulnerabilities that detected by the black box tool. And then in testing frameworks, this is going to be very exciting. So if in your product you have unit testing, Slim testing, or any testing suite, great. All of those are going to incorporate it into Ravage and turned automatically into security test. So you just double the size of your security test cases. Because all of those, as long as they have rules running on top of Ravage, you will detect security vulnerabilities. Testing environment. So in testing environment, if in your application, in your company, you have staging servers, you have dev servers, you can ask your devs and QAs whenever they're testing their application on that server, run that server on top of Ravage, so that whenever they're using that server, they're actually helping you guys for security testing automatically for free. And that production, I would proceed with caution, mainly because there's performance impact, and fully aware of that. But if you're ambitious enough, I will tell you there's a really big benefit, one big benefit that you can get by running in production, which is you're able to block attacks in real times. Think about if there's a SQL injection in your product. If the attacker is able to launch it, you're going to lose your data. But if you run Ravage to block it in real time, you're not. So that's a really great benefit. If you do want to run in production, I would say start with sampling, maybe 0.1% of your customers, and go from there and see how that works. But it's one of the options that you can have. So I'm going to talk about what you can take away from the presentation. So suppose you just forgot everything I've just said. That is okay. I have a one-sentence summary of what is RAVAGE. RAVAGE is a Java runtime analysis tool that's able to detect vulnerabilities, gather data flows, and generate exploits. And we need your help on improving its performance, especially on making JIT compiler works with RAVAGE. And also, at the end of the day, if we can contribute back to Java or OpenJDK, we can make it available to more people and the regular developers to use it. And then we also need your help to build a rich rule set. As I talked about, we have only very limited rule sets, so we might miss issues. And this is not only useful for RAVAGE or to only runtime analysis. It's useful to all kinds of program analysis tools you have. So if in the security community, if we can have a rule set that everybody shares and use in different products and different tools that does program analysis, I would say that's great. It's really valuable. So we are trying to push that. And since the knowledge with RAVAGE is not language specific, if your company is using other languages, great. We encourage you to implement RAVAGE to other languages as well. So because the demo failed, I actually ended up early. And that's not expected, but that's OK. So thank you for being here. I really appreciate it. And thank you for your patience. If you want to download a tool, slides, white paper, and source code, go to ravagesecurity.com. So thank you, guys. And open to questions if you have them.